Okay, this is Physics 1A for March 17th, and today we're going to talk about relative velocity. I think at the end of last class I said we would just be doing some more projectile problems today, but I forgot that this chapter also includes this topic, and several of your homework problems, you're going to need to know how to handle this. So we'll get started with this. We'll do one relative velocity problem, and we'll probably do one projectile problem, and if there's more time, we'll do some more. Okay, so relative velocity. This is a concept that you probably have a good idea, a good intuition for. So, for example, if let's just take a really simple example. Let's say you have two people that are in a cars that are traveling in opposite directions. So you've got one car called car A, and I've got another car that I'll call car B, and they're approaching each other. So car B is moving in this direction with a velocity, let's say that we call let's just use miles per hour, 60 miles per hour west, right? And let's say that car A is moving in this direction with a velocity of 40 miles an hour to the east. And I ask the question, how fast does it look like B is approaching from the perspective of A? What's the answer to that question? Oh yeah, Kelvin took him for 2A, so highly recommended, yeah. How fast does B appear to observer A? So just think you're driving down the road, you're going forwards, and you see a car approaching you. How fast does it look like it's coming towards you in a situation like this? Faster than 60, right? Maybe twice as fast. 100 miles an hour. What do other people think? Anyone else want to make a guess? It's okay to get it wrong. Questions like this are just really just to kind of test your intuition. 100? Okay. Twice as fast. Okay. So definitely everyone agrees that B is going to appear to be moving faster than 60 miles an hour. So everyone agrees with that. Some people think it'll be twice as fast, like 120. Some people think it'll be 100. And the answer is that it would be, you're all pretty close. The answer is 100. It is 100. So the answer is 100 miles an hour. And the reason why is because since you're moving to the right at 40 miles an hour and they're moving towards you at 60 miles an hour, the rate at which the cars are getting closer together is basically 100 miles an hour, if you think about it. Because when you're riding in a car, you can perceive your own motion by looking left and right, or you can perceive your own motion by looking at another car. But if you were to compare the rate at which the road is moving, like if you look left and right in your car as you're moving 40 miles an hour, the road should be moving backwards, and the things like trees and stuff on the side of the road should be moving backwards at 40 miles an hour, right? You're moving forwards, so anything that's near you is going backwards at 40 miles an hour, right? But all those things are kind of at rest relative to the Earth. So if there's something that's also on the Earth and it's moving at 60 miles an hour towards you, then you have to add those two velocities together, right? That's how you got 100, right? You took 40 plus 60. And if the numbers were like 30 and 20, you'd add those together, 30 plus 20, and you get 50. So you all have a pretty good intuition that at the very least you all understood that car B looks like it's going faster, and most people seem to know that the answer was 100 miles an hour. Right? Let me give you another example. So what if we have two cars that are going in the same direction? So we'll leave car A going the same speed. So let's say car A is going at 40 miles an hour. And let's say that there's a car that comes along and passes car A. Call this car C. And we'll say this is also moving to the east. Let's say that a car passes car A, and it does so at a velocity of 70 miles an hour to the east. And you ask, again, how fast is C passing A, you might say. Or you could just say, how fast does it look like C is going for A? 30, exactly. So that's the rate at which C is kind of approaching and passing car A, right? 30 miles an hour. This person's 30 miles an hour faster, so that's the rate at which they're going to overtake and pass them, right? So for that, you took this velocity and you subtracted this velocity, right? So how can we kind of compare these two ideas? So in the first case, you added the velocities. In the second case, you subtracted the velocities, right? Well, it turns out you're doing the same thing in both cases. It's just that in the first case, velocity B was actually kind of negative, basically, right? So you could think of it as doing like 40 minus negative 60, for example. Okay. So we want to develop an intuition for how these type of things work. We want to have an equation so we don't have to kind of guesstimate or think about what it is. And then we want to understand how it works in two dimensions, basically, right? So let's do that. What we'll do is we're going to consider how this looks from two different reference frames, okay? And that word reference frame has a specific meaning. So a reference frame is the way in which one observer views the world. It's like their setup, their own coordinate system, basically, right? It's like one observer's view of the world. And it can be made into a coordinate system or be represented by a coordinate system. So right now, we all have our own reference frames, okay? You're all probably sitting down, and you're watching what we're doing here on a screen of some sort, whether it be a mobile device or a laptop or a computer, whatever. So your reference frame is defined by that. You can think that you're at the origin of your own reference frame and your own coordinate system, so to speak, and you could imagine that you could measure distances relative to yourself. Each of these observers that we described up here, A, B, and C, they also have their own reference frames. The difference between you, who's sitting still, and them, who are moving, is that they carry their reference frame with them. So you could think that there's kind of like a coordinate system, an XY coordinate system that rides along with person A. And there's an XY coordinate system that may look a little bit different for B. Maybe it goes in this direction. Maybe for B, the positive X direction goes to the left, like this. And relative velocity is all about coordinating between one reference frame and another reference frame, basically. Okay? And so that's how we're going to kind of set it up. So we're going to draw two different coordinate systems, one that's kind of at rest relative to the Earth, and one that's moving relative to the Earth. So we're going to have one coordinate system like this. Just going to make it really long. On top of it, I'll put another coordinate system. One of these coordinate systems will be moving, and the other one won't be moving. So there's the second one. We'll make that one green. So each one of these is a coordinate system, and they're going to be for two different observers. I'm going to call the observers observer A, and we'll call the green observer observer B. And like I said, they each have their own coordinate system, so this is going to be the, this is the X direction for observer B, and I'm going to call it X prime. This is the Y direction for observer B. I'm going to call it Y prime. This is going to be the X direction for observer A, and it continues in this direction as well. And then this will be the Y direction for observer A. And what we're going to do is we're going to look at how each of these observers see some type of event, some type of thing that's happening, okay? And the difference between the two observers is that the B system is going to be moving, okay? So we'll throw on here a little vector and say that the B coordinate system is moving with some velocity. And the way that I'm going to label that velocity is I'm going to say that this is the velocity of observer B relative to observer A. So that's what that symbol means. I'm going to write over here. I'm going to write that over here so that you're clear with what the notation I'm using is. So VBA is going to represent the velocity of observer B relative to A. And that word relative to A, okay, that phrase relative to A means as measured by observer A. Does that type of notation make sense to you all? Does anyone have any questions about what I mean by that? So this is the scenario. Observer A is sitting at rest. Maybe this is just a person standing on the side of the road. Observer B is like in a car or something, and they're moving at a constant speed in a constant line away from observer A, right? And they have a constant speed, all right? This velocity is not going to change. So this velocity, VBA, is going to be a constant, all right? But that's kind of the setup. We have one observer A that's at rest relative to the Earth. We have another observer B that's moving to the right, and these red and green coordinate systems are the way in which they observe their world. All right. So now what we want to figure out is, suppose that there is some event that occurs. Maybe there's some explosion off in the distance. Maybe there's another car that's moving along on a different road or something like that. And we're going to just label that with kind of a little star right here. And we're going to say that it occurs at point P. Okay? So at point P, there's some event, all right? And that event itself is also moving, okay? And what we'd like to know is, what is the velocity of this motion relative to observer A? And what is this velocity of that motion relative to observer B, okay? So P is something that's happening and it's moving. It could be a star that, like a shooting star. It could be a plane flying through the sky. It could be really anything. But this thing is something that's moving, okay? So P is another thing that's moving. Okay. So in order to understand what the velocity of P is, and here's what we want to figure out. What is the velocity of P relative to A, okay? So I'm using that same notation that I used up here. So this is what we're going to try to find out. And VPA is going to represent the velocity of P relative to A. And we'd also like to do basically the same thing for B. So we'd also like to be able to find, for example, the velocity of object P relative to B. We'd like to be able to do those two different things right there. Okay. So here's how we're going to do it. In order to understand velocity, we need to first understand the position of such an object. So the first thing that I'm going to do is I'm going to draw a vector from the origin of A, here, out to point P, and say that that's going to be the coordinate, or the position, of P relative to A. So R we use for position, right? This vector means position. That position is usually probably going to be described by using coordinates, right? So there's going to be an xy coordinate for point P, and we can turn that into a vector. All right. The next thing we'll do is to draw a vector to represent the position of object P relative to observer B. So that will be labeled as the position of P relative to B. All right. And then we need one other vector to draw in here. And I think I'll use black. And that is going to be the vector that connects between the origin of B and the origin of A. So that vector we'll call... does anyone want to make a guess what we're going to call this last vector that I just drew here? So observer B is located at the origin of his own coordinate system, and that observer is moving to the right with a constant speed. Observer A is located at the origin of their coordinate system, and that observer is at rest relative to the Earth, right? If I draw a, RAB, what is that it? Let's see. It's not exactly right. You got to switch them. I know this is tricky, so I'm glad I asked you because that makes it clear to me that I'm not being super clear. This is going to be the position. So you start from A and you go to B, right? This is going to be the position of observer B relative to A. And I think if you look at each of one of these, it's always the same. So notice that when I drew the vector from A to P, I called that the position of object P relative to A. So the thing that is second is always the observer. That makes sense. And then let's just go through each of them. For B, we said this is the location of B. Sorry. This is the location of P relative to B, as in boy. So the observer is always second. Or it's not always going to be an observer. It could also just be something that you're talking about. It could be the earth, the wind, a river, different things like that, right? So now we've got this really nice vector diagram. We can really quite simply talk about what the position of P relative to A is compared to these other two vectors, right? Because since they're added tip to tail, I can write down the following vector expression. The position of P relative to A should be equal to this vector down here on the bottom. I'll keep the color coding going. The position of observer B relative to A plus the position of, oops, that's the one that I want to turn green, right? So plus the position of P relative to B. Can everyone see, like, in terms of vectors, that that's true? This vector plus this vector is equal to the vector that joins the first one to the end of the second one. That's just our definition of how vectors work, right? Okay, so the next step is really simple, and we'll immediately get to what we wanted to prove from this. The next thing we do is we just take the derivative of the whole expression. The derivative with respect to time. So what we end up getting is the derivative of the position of object P relative to A with respect to time should be equal to the derivative of this plus the derivative of this. And when we take the derivative of the position of an object, what do we get? If I take the derivative of the position of an object with respect to time, you get velocity, right? So we're going to call this the velocity of P relative to A is equal to the velocity of B relative to A plus the velocity of P relative to B. And now we've actually solved for this, and technically we've solved for this too. Okay. I'm going to write this in a slightly different way, but this is our final answer effectively. I'm just going to rearrange things a little bit. I'm going to write it as VPA is equal to VBA. Nope, that's the same way. I'm going to put this one first. VPB plus VBA. So this is the relative velocity addition formula. We call this the Galilean. Galileo has two L's somewhere in his name, right? Is it Galileo? It's probably here, right? I don't know. Galilean relative velocity addition. this tells you, given two different observers that observe the same event, how do you compare the velocity that B sees to the velocity that A sees? That's what it says, basically. That's what it says. You always need to have three different things that show up here. If you look at the way the equation works, I think that it should be relatively easy to remember or understand. The way that I look at it is, if I want to know the velocity of P relative to A, what I need to do is figure out the velocity of P relative to some other point, and the velocity of that point relative to A. So notice that, just look at this. You've got a P, right? And here you've got a P. And then you've got, over here you've got an A, and here you've got an A, right? And then in between, you've got the two B's that show up here and here. So as long as you write it like this, I think it's easy to remember, because it's like, to get VPA, you need VPB and then VBA. The B, I think of it as like, you kind of think of these two terms here as like squishing together, and the B's kind of cancel out or merge together or something like that, if you guys can see that. If you all can see that. So we call this Galilean relative velocity addition because it was first kind of written down or understood by Galileo. I think other people probably understood this before him, but this is the name that we give to it. And the reason why we don't just call it relative velocity addition is because Einstein figured out that when you go really, really fast, this doesn't work anymore. This is no longer true. We'll talk about that here in a little bit. So let's apply this to the first example that I gave, okay? So let's say that we are talking about two cars that are moving, okay? So now I've got car A. I've got car B. Let's use the same numbers we used at the beginning. So the first one was that this one was moving at 100 miles an hour this way. And this one was moving, no, not 100, sorry. It was 60, right? 60 miles per hour. And I think I did. I want to use the same numbers exactly. So it was 40 and 60, right? Now here's the thing about using this equation. You're not going to be told what is object A and what is object B and what the third thing is. So you need to figure out for yourself what those things are, right? And the way that you do that is you have to think about what this velocity actually represents, okay? So let's step back for a second and try to understand something about velocity itself. There's no such thing as an absolute definition of what velocity is, okay? So for example, if you're driving along the road at 60 miles an hour, right? What does that 60 miles an hour represent? What do you mean? When you say you're driving down the road at 60 miles an hour, what do you mean by that? The speed that someone is seeing you go. I'm glad that you said that, because I think we found by, considering what's happening here, that different people could observe you moving at different speeds, right? So if I'm moving at 60 miles an hour and there's an observer standing on the road, the observer would agree that I'm moving at 60 miles an hour as long as they're standing at rest, right? However, if there's a car that is moving towards me, that car is going to observe me moving faster, right? So different people can observe you moving at different speeds, right? So again, I'll ask, when I say you're moving at like 60 miles an hour on the road, what does that speed mean? It's not the speed someone is seeing you go. Not necessarily. Not unless they're sitting at rest on the side of the road. It does mean every hour you advance 60 miles an hour. Yep, that's right. But all velocities are relative. And when you say 60 miles an hour, you mean the speed relative to something, right? It has to be the speed relative to something. So what do you mean when you're 60 miles an hour relative to what? To the Earth. That's right, Kelvin. And maybe that's what Tom Bui meant when he wrote RBE. I don't know what that's supposed to mean, but maybe he meant the Earth. I'm not sure. Yeah. When you say 60 miles an hour, you're going at 60 miles an hour relative to the Earth. Are you moving at 60 miles an hour relative to the sun? Are you moving faster, slower? The Earth moves around the sun very quickly, right? And you ride along with the Earth, right? Yeah, that's right. You'd have to take into account the Earth's speed, Kelvin. That's exactly right. So if you want to know your velocity relative to the sun, you would need to take into account the fact that the Earth is also moving, and then you'd need to add your velocity relative to the Earth plus the velocity of the Earth relative to the sun, right? You would take the velocity of your car, let's say, relative to the Earth, plus the velocity of the Earth relative to the sun, and that would give you the velocity of your car relative to the sun. You see how it's the same equation, basically? These two equations, you can compare them. They're basically the same, right? And then you can go even farther. You can say, what's your velocity relative to the center of the galaxy, right? Because then the sun is orbiting around the center of our galaxy, and if you wanted to find your velocity relative to the center of the galaxy, you'd have to include the velocity of the sun relative to the galaxy as well, because of course the Earth is being carried along with the sun. And you can keep playing this game. You can go even farther. You could say, what's your velocity relative to another galaxy like the Andromeda Galaxy? And there's really no limit, because there's no point that you can compare to say, like, that thing is at absolute rest. There's no point in the universe that is absolutely at rest. Everything's moving, and everything's moving relative to each other, you know? When we look out in the night sky, for example, and we look at all the different galaxies that we can observe with our telescopes, it looks like the vast majority of them are moving away from us. And some of them, though, are moving towards us. And those are all based on relative velocities. Those are velocities relative to our observation. And an observer looking at the night sky from a different solar system, they might see something different. Or maybe they would see exactly the same thing. So yeah, all velocities are relative. Keep that in mind. And when you say a velocity, you need to define what that velocity is relative to, right? Okay. So yeah, we got to actually try to figure out how to apply this equation to this situation down here. And in order to do that, we need to redefine what these velocities are, okay? So what I'm going to do is I'm going to say the 40 miles an hour, just like you all said, was the velocity of car A relative to the Earth, right? That's going to be positive 40. This is going to be the velocity of car B relative to the Earth. And what I'll do is I'm going to call this direction positive x. So if I want to say velocity of A relative to the Earth is 40, well, then what would the velocity of B relative to the Earth be in that same coordinate system? So now the Earth is our coordinate system, negative 60 exactly. Now, my original question was, how fast does car B look like it's approaching car A? So that would be the velocity of, is it going to be B relative to A or A relative to B? If I want to know how fast B is moving from A's perspective, do I write VBA or VAB? Again, I want to figure out how fast does this person see car B move? The velocity of, so the velocity of B relative to A. How does A see B moving? Okay. Now, according to my equation up here, all I need to do for this is to write the following down. I'm going to write V. I take the first symbol here, which is B. I take the common thing, which is E. And then on the second term, I write V. I put the common term E first, and then I put the A. Are you guys following kind of like how I'm figuring what to put there out? It's like first is going to be B, second is going to be the one that they have in common, and then third will be the second variable that shows up over here. Okay. But now we have a problem, because I have VAE, not VEA, right? But how can I connect them? There's a connection. This says the velocity of the Earth relative to A. What would that be? If I say the velocity of A relative to the Earth is positive 40, that's right. What Ton said is right. It's just going to be the opposite, right? So that actually gives us a general thing that we can write down right here. If I know the velocity of some object relative to a fixed point, it doesn't even have to be fixed, then this is equal to the negative of the velocity of EA. So basically, if you want to switch these variables down here at the bottom, you get a negative sign out of doing that, okay? And that's because if I'm moving to the right at 40 miles an hour, then it looks like the Earth is moving backwards away from me at the same speed. So what we can do is, there's two different ways we can do this. What I'm going to do is I'm going to take this one and say that we can rewrite that to say that VEA is equal to negative 40 miles an hour. And now we have the two things that we need to put into our equation right here. So what we end up getting is the velocity of object B relative to A is equal to VBE, which is negative 60, plus VEA, which is negative 40, and our answer is negative 100, which is exactly the answer we got from above by just kind of thinking about it. So your intuition works just as well as this equation does. There are also relative accelerations. They work exactly the same. We will see those show up in the next chapter. But there we go. Anyone have any questions? So I mentioned Einstein. I'm gonna mention it again. So one of the questions that maybe Jonathan has a question before I say something about that. Oh, sure. Okay, so Einstein supposedly, as a kid, asked the following question. He was curious what it would look like if you were traveling in a spaceship that was moving really fast, and someone were to you were to see another spaceship coming towards you, and you wanted to measure the rate at which that spaceship was moving towards you. Okay, so this was the kind of thought experiment that Einstein used. So he took two spaceships. So we've got one right here. We've got one over here. Really crude spaceships that I'm drawing here. And he said, suppose that this spaceship is moving in this direction with the velocity of light. Okay, so the velocity of the spaceship on the left is c. Okay, the symbol c stands for the speed of light. Okay, so c is the speed of light, the rate at which light moves. In case you don't know, light does not move at a instantaneous speed. You know, when you turn on the lights in your room, for example, the entire room becomes illuminated pretty much instantly, right? But it actually takes time for light to travel between 2 points. So light from the sun, for example, takes about 8 minutes to get to Earth. It takes about 8 minutes for the light from the light from the sun to get to the Earth. Which means when we observe the sun, we're actually looking at what the sun was doing 8 minutes in the past, right? And the farther things are away from us, the longer that the light takes to get to us. So when we're looking at galaxies that are, let's say, 1 million light years away, a light year is the distance that light travels in a year, we're looking at what the galaxy looked like 1 million years ago, right? Because it took time for that light to get to us before the information got to us. So we use the symbol c to represent the speed of light because it's a constant. It doesn't change. So this is what Einstein thought about supposedly as a kid. Suppose that I have a spaceship that's moving to the right with velocity c, and it sees another spaceship. We'll call this one A, and we'll call this one B. It sees another spaceship that's moving towards it with a velocity of negative c. All right, so it's moving to the left, basically. Right, one's moving right, one's moving left. You could ask again, what's the velocity of B relative to A? Now, according to what we just said, what would the answer be? According to Galileo, what would the answer be? And if it's hard to think about this, just turn them into numbers. If this was velocity was positive 100 and this was negative 100, yeah, it'd be negative 2c, right? Okay. Twice the speed of light, right? This bothered Einstein as a kid, I guess. I don't know how young he was when he was thinking about this. I don't know if he was in high school or if he was, like, really young. I think he was in grade school. But I may be wrong. I don't know. I have to go read about it again. So he felt like that was kind of weird because then, you know, the velocity of light in every experiment that we've ever done appears to be constant. It appears to be the same. So if I had an object, such as a spaceship that was moving at the speed of light, and someone else saw that spaceship, then according to all measurements we've ever done, this doesn't make any sense. According to Einstein, the observer A shouldn't actually see this. He should instead see this. That's what should happen. You can't go faster than the speed of light. You can't observe someone moving faster than the speed of light. It's just impossible to ever break that kind of barrier. So this equation doesn't work when you get really close to the speed of light. That's what Einstein figured out. And he used it to develop a theory that's called the special theory of relativity, which is one of the kind of biggest kind of overhauls of old physics, you might say, of classical physics. And he did so by making the assumption that all observers measure the same speed of light, which was a pretty groundbreaking assumption that then allowed him to show all kinds of crazy things about how our universe works, about how space and time are intricately related to each other, and how fast you move alters how fast clocks tick. Have you all heard this before? That if you travel really quickly, that clocks will tick slower. Has anyone heard that before? I don't think it's very well known. Yeah, Interstellar heavily deals with this, right? They call it time dilation. And whether you know it or not, so Interstellar deals with it in a different way because it turns out that gravity also can mess up time. So basically, clocks tick slower near the surface of the Earth than they do up in space. Okay? Not by much, by like a nanosecond or something like that. But in the movie Interstellar, they were near the surface of a black hole, right? Or they were on a planet. They went down to some planet that was like covered in water, and it was near a black hole. And so I think it was something like when they went down to the planet, every hour they spent was like 7 years or something like that. Up on the... Yeah, so everything's relative. So we started this talking about relative velocity, and we saw that, you can have different velocities. Different observers can disagree on the velocity of an object. Well, it turns out that if you take it to an even bigger extreme, like Einstein did, and start looking at things moving close to the speed of light, then the rate at which their clocks tick changes too, which is pretty cool. And that, of course, makes for some really good science fiction, and it also opened up new ideas about how our universe works. Okay, so if you want to learn more about that, you can take Physics 1D, or you can just go read about Einstein. Go read about special theory of relativity. It's pretty cool. Some neat things happen. All right, so let's look at an example problem of a boat crossing the river. Two parts on this one. So, a boat crossing a wide river moves with a speed of 10 kilometers per hour relative to the water. The water in the river has a uniform speed of 5 kilometers per hour due east relative to the Earth. If the boat heads due north, determine the velocity of the boat relative to an observer standing on either bank. And then it says, if the boat travels with the same speed of 10 kilometers per hour relative to the river, and is to travel due north as shown, what should its heading be? All right. So we're going to redraw these pictures here. I hate it when these... Well, I should really block out this picture or something so we can draw our own, but it's still good to have it to compare to the drawing that I made. So what we have going on here is we have a river, and the river is moving east. Okay, so let's make a little trough here for our river. So that's our river, and the river is moving to the east. At a speed of... It says the water in the river has a uniform speed of 5 kilometers per hour due east relative to the Earth. Okay? So what I'm going to do is I'm going to call that the velocity of the river relative to the Earth. And it says that it's equal... It's a vector, by the way. It says that it is 5 kilometers per hour. So I'll write 5 kph. And since it's east, what I'll do is, since these are vectors, I'm going to say this is the positive x direction, and this is the positive y direction. So we'll drop an I hat on here. So that's going to be our east direction is I hat. So the river's moving like this, and we have a boat that wants to cross the river. And so we're going to put a boat in here. So here's our boat. The boat is, what does it say? It says, if the boat heads due north, determine the velocity of the boat relative to an observer staying on the river. And we also know that the boat moves with the speed of 10 kilometers per hour relative to the water. Okay. So our boat is, we're going to need a vector for this one. So our boat is moving in this direction, straight north. And we'll call that the velocity of the boat relative to the water or the river. Because it says it's 10 kilometers per hour relative to the water. That's also a vector. And I'll write down here that that's the velocity of the boat relative to the river. And it's equal to 10 kph. And because it's moving north, I'm going to drop a j hat on here. In all of these relative velocity problems, there are going to be 3 objects. And the key thing to do is to just identify what those 3 objects are. In this case, the 3 objects are boat, river, and earth. The very first homework problem that you have, there's these 2 tanks that are moving towards each other. In that case, there's going to be 3 objects. There's going to be tank 1, tank 2, and the earth. And you'll need to use those to set up that problem. That problem involves kinematics, but it also involves projectiles. Alrighty. So our goal here is to figure out if the boat heads due north, determine the velocity of the boat relative to an observer standing on either bank. So we've got an observer over here, okay? And because this is an Earth-based observer, we're just going to call our observer E, all right? And our goal is to calculate what is the velocity of the boat relative to the Earth. Now we can see this from a vector picture as they've drawn here, because we know from our velocity addition formula above that if I want to find the velocity of the boat relative to the Earth, all I need to do is to find the velocity of the boat relative to some other thing. The other thing in this case will be what? River, right? So the velocity of the boat relative to the river plus the velocity of the river relative to the Earth. And if we add those 2 things together, then we'll get our answer, right? Well, we know how to add vectors, and we have VBR right here. All we need to do is to add in VRE into our picture. And the way we normally add vectors is by adding them tip to tail. So we'll just start right here. Draw a little vector like this. We'll make it blue for the water and say that that's our VRE. Right? And then to find our final value here, VBE, if I want to know how fast this person sees the boat move, I just need to connect tip to tail. We're going to complete this triangle right here. And that third side will be the velocity of the boat relative to the Earth. I don't think we need to do any changing of these signs because this is already set up how we want it to be set up. So all we need to do is just literally put these in here. Velocity of boat relative to Earth is going to be equal to VBR, which was 10, J hat, plus VRE, which was 5, I hat, and then all of that is measured in kilometers per hour. And that is technically the answer. Yeah, I mean, that is the answer. It just says to determine the velocity. Now, what we want to do also probably is find the angle, because we're going to want to compare that to what happens in part B of this problem. So let's find the magnitude of this. To find the magnitude of VBE, what do I have to do? To find the magnitude of that vector. Yep. Square each component and take the square root. So it's 10 squared plus 5 squared, which will be like 125. We square root it, and the answer is going to be in kph. The square root of 125 is probably going to be something like 11 point, I don't know, something. Let's see. 5 root 5. Yep. Oh, yep. There we go. 11.2. Okay. Everyone agree that it's 11.2? And then if I want to find the angle that is labeled as theta, in our problem, that angle is this right here, theta. Then we would take VRE over VBR. So theta is going to be equal to arctan of 5 over 10. I think this is something like 26 maybe. Yeah, 26.6. Okay. So however you want to put your answer, this is magnitude and direction, or you can write it as a vector like this. Does anyone have any questions? These problems can be incredibly difficult, or they can be really easy. If you just remember how to use this formula, and that there's always going to be 3 things, and you take your time, it can be very easy. If you try to jump to the solution and try to figure out how to solve that way, it's going to be hard. But if you just take your time to write this equation out, think about what each of the things are, and do it properly, it will be very easy. Okay? That being said, when you see these kind of problems, I know personally when I was a student and I would see these relative velocity problems, I would get extremely confused. And so I understand if you do so, but just remember it's not super complicated. It's just more about setting it up and taking time. All right. Part B. If the boat travels with the same speed of 10 kilometers relative to the Earth and is to travel due north as shown, what should its heading be? So now the question is, if you want the boat to actually go north, so we saw that the boat basically traveled along kind of like this. Oops, I want that to be black. The boat basically travels kind of like this. It's facing forward, but it's being carried along to the right. So let's say, for example, that you wanted the boat to take off from this location and you actually wanted it to end up due north. All right? Would you all agree that the boat has to basically head off to the left? Yeah. Okay. So now what we're going to do is we're going to angle our boat this way. We angle our boat off that way. And now we'll draw on our vectors again. So we're going to have the velocity of the boat relative to the river is going to go this way now. And the velocity of the river relative to the Earth didn't change. The river is still flowing to the right, so it goes like this. And then those 2 vectors should add together to give us a vector that goes straight north, which is what we want from here to here. And now we're just going to write our vectors in again. So this was VBR. This is the velocity of the boat relative to the Earth. And then finally the one on the top, which you can't really see. Let me move it down just a little bit. There we go. This would be the velocity of the river relative to the Earth. Okay. And now the question is, if the boat travels with the same speed and is to travel due north, as we've shown, what should its heading be? So now what we want to know is what this angle right here needs to be. Let's call it phi. That's what we want to figure out. All right. So my first question is, do you think it's going to be the same as this? What do you all think? Is it going to be the same? No? Okay, why not? Let's see. So the velocity of the river relative to the Earth is 5, right? So we basically have a triangle like this. It's 5 on that side. We're trying to find the angle phi. And the velocity on this side over here is the velocity of the boat, which is 10, right? And so now we want to find the angle phi right here, right? So we can do a little, sine inverse, exactly. So if we do the arc sine of 5 over 10, that'll give us the angle phi. And I think this is going to be something like 22 probably, or something like that. I don't know. Let's see. Wait. 5 over 10 is a half. So it's going to be 30, right? Yeah, it's 30. I'm being silly. Thinking about a problem from the other textbook. This is from a different textbook. 30 degrees. There we go. And that's relative velocity. Anyone have any questions? Okay, so again, just this can be very tricky, but you take the time to identify what the 3 objects are, write down that equation, fill in information, then it won't be too challenging, I promise. So it's 2:57, and I'd like to do at least one more projectile problem, honestly, if that's okay with y'all. If you need to go, you can go. I'll put this all up on YouTube, of course. I might want to stop the recording for a second.